Yogi Chino from阳明交大 University. He will talk about random walks in cooling random environments.
Thank you very much for nice organizing, and also thank you very much for the nice introduction. And I'm really glad to have such kind of opportunity to give a talk here. Okay, so first of all, I need to have a self-introduction. My name is Yuki Chino, and Chinese pronunciation is千野由喜, and Yoshi sounds like this letter. Actually, my Yoshi is this one, but someone understands the pronunciation is the same as this one. So then my friend called me Mr. Pregnant. Yoshi means some kind of pregnant, right? Okay, anyway, so today I would like to. Okay, this is not a self-introduction. Okay, and okay, so I came from National陽明交大University. Now the name is too long, so NYC. And also the Department of Applied Mathematics. And basically I work on probability theory and statistical mechanics. Statistical mechanics is one kind of the physics. And today I will talk about random walk in cooling random environment. This is some kind of the application of the random walk in random environment. So this is today's meaning of the talk. The first section, I will give you some introduction, and I just introduced random walk. This is quite a basic probability theory, and I try to introduce some kind of application of the random walk to the heat equation. I just show you some connection between the probability theory to the PD theory. And also this disordered model, because today we consider random walk. This is a stochastic process, and with random environment means a random process on random environment. Such kind of the model we call the disordered model, because we have two randomness, and two randomness interact each other. So then we can find some kind of disorder. Okay, and the second part is the main part. I will introduce the random walk in random environment and motivation and definition, and the remarkable results I will tell you. And after that, this is the main part of today's talk. Random walking, cooling random environment. Actually, this cooling random environment is one kind of the random environment with dynamics. And I also tell you the motivation and definition, and also the main result of our work. And in the end, if we have the time, so I just tell you the summary of this talk. And this result is based on the work collaboration with Professor Luca Avena and Professor Franken Hollander. They are professors in the Leiden University in the Netherlands, and also with my best friend from Brazil, Conrado da Costa, and now he works in Durham in the Britain, Durham University in the Britain. So this is the main work when I was in the Netherlands as a postdoctor for 2.5 years, and after that, after I came to Taiwan, and still we work together, and then finally we finished this project. Okay. The first part is introduction. If you listen to the words random walk, what kind of the things you imagine? I think a lot of guys imagine there's some kind of the process of the stock prices, right? Because in Taiwan now the economics is very good, thanks to the TSMC. Yeah. So then my friend, actually my Korean friend, actually he works in Taida, and he bought a lot of stocks from the TSMC, and yeah, he looks like now like that. And probability theory, one application is economics. If you study the random walk and continuum limit Brownian motion, so then you can apply some economical part. And second one is I just write a DNA chain. Maybe why I wrote here, later you can understand. So maybe in 10 minutes or 15 minutes you can understand. Okay, so first of all, so let's define the random walk. First we consider the path. Capital S is equal to start from S0. S0 is a starting point, and S1 is the first step, the position of the first step. S0 and next step is S1, S2, right? Such kind of the sequence we call path. And each path has some kind of weight. And how to define the weight is this one. Use a one-step distribution we call. And this one-step distribution D, you can choose. For example, if you consider the nearest neighbor model, means I'm here, and the next should be just one step. Next is one step. This is nearest neighbor model. Means 1 minus x is equal to 1. Right? This is indicator. If this occurs, 1. If this doesn't occur, 0. So this model you cannot jump 2. You cannot jump. Every time you just jump one step. Right? This is the nearest neighbor model. If you choose D like this is a D-dimensional case. If you consider one-dimensional case, it's just a 1/2, right? Because you only choose right or left. Right? And the long-range model, you can, okay, so I allow you to jump a bit longer. And then, but my jump ability is not so high because I'm so old now. So then, around here is fine. High probability I can jump. But if x and y is far from each other, so then the decay polynomially. So it means longer distance jumping is difficult, right? But still polynomially decaying. Or also you can say exponentially decaying is exponentially dumping. You can also define. Anyway, so choice of the D is up to you. So you can tune any kind of the random walk if you want to think. But in this talk, we consider the dx means start from 0 and the next jump is x. If x is +1, because now we consider one-dimensional. Go to the right, jump. This is a probability p. Jump to the left. This is a probability 1 minus p. Quite simple case. Let's think about it. And especially this p should be 1/2. 1/2 is much easier. Means symmetric. Jump to the right, 1/2. Jump to the left, also 1/2. Right? Yeah, actually, I really like Taiwanese beer. So you understand here is Taiwanese beer. So after you drunk, maybe you can perform like this random walk, right? And starting the random walk, one topic or what we are interested in is recurrence versus transience. What is the recurrence? What is the transience? Our real interest is after we got drunken, can we go back to our home or not? That is a very important problem for a drunken guy. And then this simplest case, if D is equal to 1, D is equal to 2, recurrent means you can go back to your home infinitely many times. Means quite safe. But bigger than D is bigger than 3, the model becomes transient, means you cannot go back. So if you live in Taipei, only flat part, you can come back. But if you live inside the mountain or something, 3-dimensional case, you cannot go back. Such kind of the result we have. So considering the random walk is really real. And from the view of the probability theory or mathematics, what we are interested in, we consider the Sn. Sn is after n steps. After n steps, where are you now? This is we just write Sn. And actually, this is a summation of the first jump, second jump, and nth jump, right? Is it okay? And this is a basic notation. And for this Sn, we are interested in such kind of the ratio. And if n goes to infinity, do we have such kind of the limit? This is we call the law of large numbers. And the second one is CLT. If we divide by square root of n, and then this goes Gaussian or something. And the last part is large deviation principle. We call LDP. This is some kind of the Sn minus this times n. Just you consider just n. This shows us the speed of the convergence. And if we have such kind of the I, we call rate function. If we have this kind of the rate function, this convergence speed is exponentially fast, right? Basically, LDP guaranteed us the speed of the convergence of the law of large numbers. Okay, so these three are some kind of the main interest from the mathematical or pure probability theory. The next is a bit different from the different side. Is from the statistical mechanics. This is physics. This statistical mechanics is what is a statistical mechanics is okay. So what is the information? Okay. So for example, if we consider PD or ODE, the differential equation. And differential equation is also some kind of the very good, very nice tool for considering the physics. For example, the Earth and the Moon, and these two stars interact each other. So then we can understand the motion of the Earth and the Moon, right? But unfortunately, we also have the Sun, the Mars, a lot of planets. And they interact each other. And someone knows three-body problems. Because if we have the interaction more than three bodies, this PD or ODE system gives us sometimes chaos. So we cannot solve the problem if we have more than three interactions. Imagine in this room we have infinitely many air molecules, right? And these air molecules hit each other, and then in this room we have the pressure and the room temperature, right? Such kind of the phenomena occurs. So how do you understand the interaction of such kind of infinitely many air molecules? PDE no longer we cannot treat. Then physicists understand, okay, we can use statistics or probability theory. Because the statistics can treat many data, right? The same way we consider the statistical mechanics is if we have the infinitely many interactions and we use it or we apply the probability theory, and then we can say something about the phenomena and then reconstruct the PD. That is the goal. Okay. And today's talk, I really want to say only one topic about the statistical mechanics. Statistical mechanicians are really interested in the phase transition and the critical phenomena. What is a phase transition? If you think about the water and okay, so the water temperature is just going down, then becomes the ice. If you heat and then becomes the vibrate, right, and then becomes the gas. maybe 100 degree and 0 degree is some kind of the threshold, liquid to the solid and the liquid to gas, right? And then these two phase, like liquid and the gas, is completely different. And then the state is completely different, liquid and gas, in between the 100 degree Celsius, right? This is what we call phase transition, right? And we're really interested in such kind of the phenomena. How can we understand such kind of the drastic change from the liquid to the gas or ice to the liquid? Because also inside the water, we have a lot of water molecules, H2O molecules, and they interrupt each other, right? This is our problem. And then in this lecture, we consider the only random walk, not the water, right? So then, do we have the phase transition and the critical phenomena in the random walk? And then the answer is yes. And if we consider this 2-point function or this susceptibility, then these two guides show us the phase transition with respect to this P. And this is just a connection to the PDE theory. If we take P is equal to 1 over 2D, then we can compute like this. So this Cnx, this means the number of the n-step random walks, right? Number of the n-step random walks. And then this P is just a 1 over 2D, and then we can compute like this. And then this is just a deconvolution. And actually, this form is same as a green function for the heat equation. This is some kind of the connection for the PDE, in one sense. Okay, so this is a bit mathematical part. We define the 2-point function like this, okay? And then we consider the Fourier transform of this guy. This is the definition of the discrete Fourier transform. And then we compute this guy. And actually, this part is equal to summation over n is equal to 0 to infinity Cn x p power to the n, right? And then we exchange the summation, this summation and this summation exchange, and then we can have the summation over x, and the summation over n is go outside, and Cn x, and we also have the e to the I k x, right? And outside p power to the n. Is it okay? This is just exchange the summation, and then this part is equal to Fourier transform of the Cn, right? So this is just a simple computation for getting this part. And using the Chapman-Kolmogorov and taking the Fourier transform, and then we can get this Cn hat is equal to C1 hat power k. So much easier form you can get. Roughly saying, here we have the nth convolution, right? Nth convolution, and then we can consider the Fourier transform of the nth convolution is just the common power n. We just use such kind of the result. And then finally, we got this expression. This is just a geometric series, right? And then easy to compute from here to here if we have the p's inside the radius of convergence. Okay. This is just a computation of the Fourier transform. And after that, if we consider k is equal to k is equal to 0, then this guy is equal to chi p. It's a susceptibility. And actually, this is just this fraction, but it's quite easy and very good expression. Because if this is p is smaller than 1 and 1 over 2d, then this guy is finite. But bigger than 1 over 2d, this guy is divergent. Okay. In this sense, we have the phase transition. This is a phase transition in random walk. And what is a critical point? Like water, 100 degrees Celsius, and 0. In this case, 1 over 2d. This is equal to the radius of convergence, right? And statistical mechanical way, so this guy is equal to P divided by PC, because the PC is this one, and the 2D is here, so we can have such kind of relation. But here, this gamma should be power 1. And physicists really care about this power, and this power should dominate the critical phenomena, we believe. Anyway, so such kind of the gamma we call the critical exponent. Okay. So for the statistical mechanics, first one, do we have the phase transition? And if we have phase transition, what is the critical point? And after that, we check the existence of the critical point, and then what is the behavior of the quantity? And then we can find the critical exponent. This is some kind of the main part of the statistical mechanics. Okay, so the last part of the introduction is the application of random walk to heat equation. Now we consider the Sn, and each jump is +1 and -1, and IID case. IID means independent, and maybe I think it should be okay. Okay, so every jump is the same as x1. In this case, let's compute such kind of the quantity. And then S1, actually the x1, so S1 is equal to x1. Takes +1, x, S1 is equal to S1 is equal to S0 plus x1. So this is equal to x plus 1 or -1. This probability 1/2. This probability 1/2, right? And then we can compute like this. But this probability is 1/2. This probability, sorry, so this one is not x n+1. This one is actually x1. This one is S1 is equal to S -1, right? But this probability also 1/2. And then we can compute like this. The point is here we have 1/2, and then now we have 2, and here is 1, and here is 2, right? And the fx +1 comes here, fx -1 is here, comes from here. Minus becomes plus. And this part is x + 1 minus x. This is just 1. And also the x minus x -1. This looks like differential, right? Actually, this is a discrete version of the derivative. And then this looks like derivative minus derivative. Again, second derivative. So this becomes a 1/2 n times second derivative, right? And then this is one-dimensional case. If we consider two-dimensional or much higher dimension, so this becomes a Laplacian. This becomes Laplacian. Okay. If we consider such kind of the object, this is connected to the Laplacian. And then function f, we take this Pnx. Pnx is after any step, the position x, right, reach to x. What is the probability? This is Pnx. Okay. Starting from 0, after any step, we reach to position x. This is the Pnx. And we consider the partial n Pnx is such kind of a difference, because this is just a discrete version. And then we can compute using this part, right? But this is obviously Laplacian. So now we got partial t ptx if we consider the continuous case. Partial t ptx is Laplacian ptx. This is for sure the heat equation. Okay. So this Pnx is a solution of the heat equation. Now we understand. Okay. The n-step distribution satisfies the heat equation. This is a connection from the random walk to the PD. And of course, we can say much more deeper things. But only one thing is why we said green function here in the two slides before, and why we use a g. This is a reason. The definition of the green function gx is a summation of the Pnx. But if we have such kind of the approximation using the COT, and then Pnx is approximately Pnx bar, and then we change t is equal to this one, we just use this change of the parameter, then we got a heat kernel, right? And then actually this Pnx is just a heat kernel. That's the reason why in South Korea, Seoul University, the people really care about how to analyze the heat kernel. This is a very big and hot topic now, because we have this connection. Sometimes it's a bit difficult to understand the random walk, because we can tune any kind of dx, right? If we consider the big jump or long-range jump, people call the Levy flight or something. In such kind of the case, what is the heat kernel, right? And if we understand the heat kernel, just go back, and then we can understand the Levy flight. This is some kind of the methodology. The point is, now we understand the connection between the random walk theory and the PD theory. If you are stronger PD theory, about the PD theory, using this methodology to the random walk theory. If you are stronger about the random walk theory, so you can use the random walk theory to the PD, like SPD or SD. This is a very good application to the economics. Okay. And another thing is the disorder system, but I almost skip here. The point is, okay, this is some kind of heat equation plus some potential, and we have the two way to introduce the random environment. One is random environment just introduced to the diffusion part, or this potential part. If you introduce this part, is a bit easier. This part is a bit easier because the annealed case becomes homogeneous, means a normal random walk case. But if you introduce the randomness here, this becomes a bit difficult. And I just say quenched or annealed. This is a really technical term for the stochastic and statistical mechanics. What is quenched? What is annealed? Okay, so you consider the grass. The grass. Grass is liquid. Did you know? Actually, grass looks like solid, but if you observe the molecule inside the grass, still moving. quite slow moving. And then the glass looks like the displacement of the molecule is like this, because they're still randomly moving. And if you break the glass, not so homogeneously broken, right? This part is easier to break. This part is a bit stronger, right? Such kind of the things happen. So glass is still moving. This is some kind of the assumption. This is a random displacement. Okay. But if you consider this room and the air molecule, and if I correct all air molecule and put here, and I just release, then air molecule diffuse and go back to the original state, right? Quite a short time. So and then easy to become this situation, right? Is it okay? Because if you breathe here, if I breathe here, nothing to change, right? You can breathe same density of the oxygen, right? Is it okay? So the problem is, which one is real world? Quenched case? Quenched case is this one. Annealed case is this one. If you consider the glass state, and if you wait 10 billions of years, then it becomes like this. But 10 billions of years, we cannot observe, right? But the air molecule, if I correct and release, easy to go this way. So move from here to here is easy, short, or longer. It depends on the speed to the equilibrium state. This implies which can describe the real world. I think glass should be quenched. Air molecule should be annealed, should be correct, right? Of course, mathematically, we have two models. But if we are a physicist or chemist, which part we need to observe, or which model we have to think? It depends on the solvent, glass or air, right?
Is it glass or glass? Like the window glass or the crystal?
Glass.
Oh.
Sorry, window glass.
Okay.
Yeah. Okay. All right. So, okay, now we go into the main part. Actually, I came from Hokkaido. So now the outside in Taiwan is really good weather, and the temperature is so nice. But still in Hokkaido, we have a lot of snow, so frozen. And why I put such kind of the picture? Actually, random walking random environment, the classical model, random environment is called frozen model. And our model is not a frozen. Our model is cooling random environment. So classical model and our applicable model is such kind of difference should we have. Then the point is, what is the difference between the classical model and the cooling random environment model? This is the main part of this book. Okay, so first of all, this now you understand why I draw the picture of the DNA chain. Because the original motivation of the random walking random environment is try to understand the DNA unzipping. When we try to copy or replication of the DNA, first we just unzip the DNA, and then just we take one piece and then just put A, T, C, Z, and then become two chains. This is a replication procedure of the DNA, right? The point is how to unzip the DNA. This is a problem they consider. And the motion of this triangle is a motion of the DNA helical. But actually, this DNA chain has some kind of the force to zip. This is a normal assumption. And then this is a bit difficult to going forward. Sometimes zipping force is stronger, then randomly go back. So then the motion itself is random walk. And also we have the AT connection and CZ connection. And the AT connection is stronger and the CZ connection is weaker. We already know. And if we consider this displacement is random, then randomly strong connection, you need to cut. Weaker connection, we need to cut. Means random walk with random environment, right? This is the first motivation why we consider the random walk in random environment. Okay, much more mathematical way. Let's see this part. Now you are position X, and then you want to jump to the right to the x plus 1 with probability omega x. In the first introduction, I just say omega x is equal to 1/2. But in this case, it depends on the place x. What is the example? Okay, I just show you some example. Let's consider such kind of the omega x. If you are position x, you have two choices. 1/3 jump to the right, or 2/3 jump to the right. But it depends on where you are. If you are here, you have to choose 1/3. But if you are here, choose 2/3 randomly, right? Randomly determined. This is a random walking random environment model. Okay. And okay, so now we understand. So jump to the right is omega x, and jump to the left is 1 minus omega x. Much more simpler assumption now we have. And each real value omega x is distributed by alpha, right? This example, alpha is easier because we only have two situations. With probability alpha is with probability 1 minus alpha, right? This is how to choose, right? This is how to choose omega x. And then we can define the random walking random environment using this form. This is just a Markov chain. Okay. And here, the most important part or most important quantity is this rho x. Rho x. This is a ratio. Jump to the left and jump to the right. If this is equal to 1, symmetric, right? And if this is bigger than 1, jump to the left, right? Easy to go to the left side. But if this is smaller than 1, tends to go to the right. So, okay, so now understand. If we understand the rho x, then we can say go to the right, or symmetric, or go to the left. But unfortunately, random walking random environment case, we don't have such kind of the situation. Unfortunately, we need to consider log rho. Of course, log rho is 0 or positive, negative. It is related to rho is 1 or not, right? But a bit more delicate we need to consider. So then the important part is we need to consider the log rho is negative, then random walker goes to the right. But if this log rho is equal to 0, random walkers can go back to the origin infinitely many times. Means recurrent, recall. And why we have such kind of condition, and what is this one? Actually, this log rho is the slope of this line. Okay. If we consider such kind of the moment generating function, then we assume that in this case, then we can write exact shape of this function ft. The interesting point is we have the part of the below the 1, and we have the such kind of s we should have, right? But if the case the case, this one, and our moment function, the shape is like this. So we never have such kind of the S in the current case. And next is we only care about the right transient and also right transients with zero speed or positive speed. This is related to the Lagrange numbers, right? Do you remember Lagrange numbers? And this is completely Lagrange numbers. But this one doesn't, because the speed is zero. This is not the expectation of the Zn, right? And from this theorem or proposition, what we need to understand is here we have the positive speed. The random walker behaves like Zn behaves like V mu times n, right? That's the reason why this V mu is speed, asymptotic speed. But here, unfortunately, Vn, asymptotically, then times n is 0, right? Unfortunately, this is sublinear speed, not a linear speed in this case. Why such kind of the phenomena happens? This is the most interesting part of the random walking random environment. Unfortunately, we have the trapping effect, means the local slowdown. What is the local slowdown?
Question?
Yes.
You have two randomness here. One is
Yes.
Every time that you have
Mm-hmm.
roll dice, and you have another randomness that is the distribution of Wx.
Yep.
Does it change in time?
Now we don't have the dynamics. First time, we fix the all position omega x, and then we just play or perform the random walk. Okay, now I'm here, and I can use omega x, jump to the right or left. And if I jump, and then here is x plus 1. So then here we have omega x plus 1, another value of the jumping.
And in your expectation, do you only average over different path or path then different distribution of the omega?
This expectation, this t mu 0 is this is we have the two randomness. We take an expectation for both. Is it okay?
And why is there no case of going to negative infinity?
If this is positive and then negative part, yeah. Okay, so now I need to explain the trapping effect. If we consider this is the DD, right? And each point, for example, here is x, and then we have the log x, and also here x plus 1. We also have the log x plus 1. And for example, if the log x is negative, then we just put it like this, because the negative. And if log x plus 1 is positive, we just put but a positive but not so big value, so then we just put like this. And then connect all the points, and then roughly saying, we have such kind of the potential curves. And then the point is, if we consider these potential curves, if we put some ball here, and this point is log is negative, so then this ball goes to the right. Right. That's the reason why we need to think about the log. And then here, and if we have a very high bar here, and then this ball just go down and go up, but the ball cannot go up this bar. So then going back. Mean this kind of the phenomena we call the trapping effect. for sure, some place we have such kind of a valley. This causes us the speed down here. Such kind of the valley causes us the speed down here. But in this case, almost all log rho is negative, so easy to go down, go to the right. But in this case, almost all cases are negative, but the rho is tend to bigger than 1. Is a lot of rho x shows us bigger than 1, means the log rho is positive, right? We have still a lot of positive log rho, but the expectation is negative. But in some place we have the valley. This is a point. This is a trapping effect. A bit difficult concept. And then we also have some kind of CLT-like theorem. Actually, this is not a Gaussian, but and also this is not the square root of n. But we have such kind of the scaling and limit v, limit distribution v. If this is the square root of n, and if this is Gaussian, then completely CLT case. But unfortunately, this annealed case is not the class of the CLT. And transient case looks terrible. But do you remember this S is we have the such kind of the moment function, and here is 1. And in this case, we should have such kind of the S, right? And the point is, where is this S? Where is this S? S is in between 0 and 1, 1, 1, 2, 2, or bigger than 2. Only you need to care about this. S bigger than 2. Scaling is the square root of n. And the limiting distribution, phi. Phi is Gaussian. Phi means Gaussian. So only S bigger than 2 case we have the CLT. Unfortunately, these cases are not CLT. Right? Actually, these are some kind of the S stable rows. S stable rows. And this arrow implies the value of S. Actually, if S is equal to 0, this related to the recurrent case. And S is 1, this is the 0 speed case. And S bigger than 1 is positive speed case, means the row of large numbers holds. And S bigger than 2, this is a Gaussian. Right? Okay. Also, we have the relativization principle for the random walking random environment, and the recurrent case, negative 0 speed case, and the positive speed case we have. And this flat piece is if these are positive, right? This I epsilon is positive. But if I epsilon is 0, so they're no longer exponential decay. Unfortunately, this part is polynomial decay. That's the reason why you cannot find the positive part. Okay. And then finally, because I only have less than 10 minutes, so this is the main part. What is the motivation of the random walking cooling random environment? Actually, cooling random environment is such kind of a picture. This is a classical model. At time 0, we fix the random environment and just frozen. We never change. This is a classical model. But cooling random environment model is deterministic sequence. We have tau 1, tau 2, tau n. And then first, time 0, we fix the one random environment and playing the random walking random environment. And at time tau 1, okay, again we choose the random environment. Next is omega 2. And then again we perform the random walking random environment, and again we choose the random environment, right? means a random walk in random environment, and the random environment has dynamics. Okay.
So dynamics fixed or
It-
deterministic or
Yeah, first of all, deterministic tau. And then, why such kind of motivation I put means here is a 9.11. This is some kind of the price of the stock. Here is some kind of the random walk in random environment. And here, re-choose the random environment and again. And then here, re-choose the random environment. So then here and here looks similar, but here and here is completely different. So we can guess the completely different environment we should have. Of course, this is a possible application of the random walking Turing random environment. That's the reason why I put it question mark. Okay. But anyway, so we have some kind of deterministic time of the sampling of the random environment. This is a random walking cooling random environment. Again, this is a frozen model, but frozen and dissolve and again frozen, dissolve, frozen. So some kind of intermediate. That's the reason why I just say cooling, not the frozen, right? But not dissolve, just a cooling. And mathematically, we can define like this, just a mimic of the random walking random environment. The only one difference is we put time n because the random environment is has some kind of dynamics. But if you see this picture, that should be much more easy to understand, much easier to understand. We have a time sequence, right? And then here we retune the random environment omega 2, and here again we desample the omega 3, blah blah blah. Okay, and the point is this part is a random environment. So this looks like Turing random environment. It looks like patchwork of the random environments, right? Okay, and then we can guess the properties of the random walking Turing random environment should be random walking random environment, right? This is our guess. And then actually the answer is partly correct, partly not correct. This blue part is correct, and the red part is not correct. We need to much more deep understanding of the cooling environment. Okay. This part shows us that if you choose the cooling almost the same time span, then we got a homogenization, because every part is the same length, almost the same length. So then we have the homogenization. But here and next is bigger and next is much bigger, exponentially or double exponentially growing, then the last part should be the dominate the system. Means random walking random environment dominates. So we should have the homogenization to the random walking random environment. Some kind of the phase transition we should have, right? Choosing the cooling time tau. This is the main message of this talk. Okay, so this is a robust, means the same as a random walking random environment. I just skip. And one answer for the question: if we consider random time tau, and then in this is such kind of the case, if the time length t1, t2, these are random. Now we consider random, but this is finite. Then homogenization occurs. But if this is infinity, then this part is dominant. Means just that we consider the random walking random environment. And then I just skip to the summary. if we consider the fast cooling means the width becomes drastically increasing. Such kind of situation, we just say fast cooling. In such kind of situation, the big width part is dominant. Means behavior is random walking, random environment everywhere. But if we have the same width of the intervals, then we call slow cooling. In this case, we can find the homogenization. But unfortunately, the S in between 0 and 2 is still open. But S is equal to 0. Recurrent case is already done, and S bigger than 2 case already done. Okay. So the last part, I just show you the why we have the phase transition. For example, this is a recurrent case. If we choose, this is a polynomially growing, right? Tk is the interval. Interval grow the polynomially. Still, we can find the Gaussian homogenization we have. This is a log TKB. So this shows us the exponential growing. Still, we have the Gaussian, some kind of the homogenization. How about a double exponential growing? Then finally we have the original case of the random walking random environment, and much more higher speed, completely V. Right? So we need to choose super fast cooling, then we can find V. But if you choose a bit slower, exponential or polynomial is still slow in this model, because we can find the Gaussian, means the homogenization. Okay? So this model shows us a lot of phase transitions. And if you want to understand the phase transitions, or this model is really, really interesting model. And still we have a lot of open problems. If you are interested in, I recommend working on this problem, such kind of problem. Okay, so already time. So thank you very much for listening to me. So 谢谢大家。
Any questions? 有什么问题？ I have a completely stupid question.
Oh, okay.
Why do you say cooling, not heating?
Oh, yeah, that is yeah. The reason is some kind of this model is a frozen model. This is a classical model, and random walk in dynamical random environment is every unit of time desampling. Such kind of the model we also have, but this cooling random environment is just the intermediate of these two models. If we tune tau, right, and every time desampling, this is in some sense heating model, but heating in between frozen. What kind of the words should be better? That's the reason why cooling we choose. Yeah.
Any other questions? If not, let's speak again.